we will talk about optimizing mobile games, but we will do it from different perspectives. I will talk from the perspective of developers, and Carl will talk from the perspective of a game platform which is used by more than half of developers all over the world. And this is a plan for the talk. I will go first through some highlights of the ARM guide to Unity. Then I will introduce the concept of local Cubemap, because it is needed to understand the new shadow rendering technique we have developed recently at ARM, and that I will present later. And finally, Carl will perform a live demo where he will show some of the most important new features introduced by Unity 5. So now, let me start talking about the ARM guide to Unity. The ARM guide to Unity was released last year during Unite Seattle, and the initial idea was to write about the experience of learning Unity from the scratch while developing small game demo with a student during his industrial placement in our team. So the guide, since then, the guide has been available for free from our Mali developer website. And in the guide, you can find a lot of optimization tips. And there is also a chapter devoted to more advanced users where you can find how to implement, for example, reflections based on local Cubemaps. But now we've got more ambitious goals. We will continue providing developers with the solution of the most common problems, but at the same time, we want to deliver more highly optimized rendering techniques to help developers improve the visual quality of their mobile games. You know that developing for mobile games, for mobile platforms, is a real challenge because it is a platform with limited resources, and we should carefully balance the resources at runtime. So yesterday, it was released, the second version of this guide. It is available for download for free in our Mali developer website. And in this new version, you will find more tips for optimizing your mobile games, and you will find there, for example, a nice chapter with a very nice description of Enlighten. As you know, the global illumination engine in Unity has been developed by Geometries and our company. You will be able to find there very interesting tips about how to access and lighten your custom shaders, which is we have used that in our latest demo, Ice Cave. I will show you a short video about this demo later. For example, you will find in the guide this kind of picture where we will describe and we deliver the full source code for implementing high efficient refraction based on local Cubemap. This is also a new technique developed recently in our team. Also, you can find there how to combine different types of reflections, as it is shown in this short video, where we are combining reflections from a static geometry, in this case from the wall and the windows, using the local Cubemap technique, and we combine those reflections with reflections rendered at runtime using a mirrored camera, and also with reflections from a distant environment from the skybox using a standard Cubemap or infinite Cubemap. So all these techniques has been implemented in our last demo, the Ice Cave demo, and I really encourage you to visit our booth where you will be able to play with this demo and see all these effects. And let me now introduce the concept of local Cubemap. We all know how to work with Cubemaps and how to access the texture from the Cubemap by supplying the vector, which defines the direction in the space. But let's think about what happens if we try to use the standard Cubemap in a local environment. In an environment with an arbitrary boundaries. For example, let's assume we got a Cubemap there. We have baked a Cubemap from the center of the environment, for example, and we got a camera looking at some spot in the boundary. In this case, our camera is pointing to the star. And let's think about what vector we need to supply to the fetching function of the Cubemap texture to get the star there. If we use the view vector, the v vector, we will not get the star The view vector is pointing somewhere to other place, to the spot in the boundary. For example, it's pointing to the smiley face. So what do we need to do? What kind of vector we need to use to fetch the texture from the Cubemap to get the star on it? In this case, if we put ourselves in the Cubemap position, in the position where the Cubemap was generated, and we look to the star, so then we realize that the vector we need to use for that is a vector with the origin in the Cubemap, and then the segment, and the end point will be the intersection point of the view vector, the V, with the boundaries of our environment. Only using that vector, we will be able to fetch the texture in the correct direction to get the star. And but the problem is how we can find intersection of that vector with the boundaries, because it can be arbitrary. The only way to do that is to simplify the problem and use a proxy geometry, in this case, a bounding box. Why? Because we know we know that it's easy to find the intersection of a vector with a bounding box, and the solution will be even simpler if the vector, the origin of the vector is inside of the bounding box. So in this case, we use a proxy geometry, a bounding box. We can find very easily the intersection point of a given vector with this proxy geometry. And then we build a new vector from the position where the Cubemap was baked to this intersection point, and only then we can fetch the texture in the right way. So at this point, we need to clearly distinguish between standard Cubemap and local Cubemap. The local Cubemap is a more complex entity. The local Cubemap is more than just a simple Cubemap. It's a Cubemap, yeah, our standard Cubemap, but we need to consider the position where the Cubemap was generated. We need to consider the proxy geometry, in this case, the scene bounding box, and we need to apply the local correction. We call that the local correction instead of a parallax correction, because parallax is not the right term to use here. There is no parallax. So, yeah, we are now working with some more complex entity than a simple Cubemap. And let's think about what will happen if we don't apply the local correction when we are using, for example, the Cubemap to implement reflections. So one of the first use case of the Cubemap was reflections. In this short video I'm showing on the right what we get if we try to implement reflections in the local environment without using the local correction. As you can see, the camera is moving, keeping constant the view vector along the surface, the reflected surface. In this case, it's a chessboard, a plane. And what happened there? We see that the reflection is constant, it's not changing. Let's try to explain that. This happened because the view vector is constant. We are dealing with reflections in a planar surface where the normal is constant. So if the view vector is constant, the normal is constant, then the reflection vector is constant. This is what we get, constant reflection. The reflection doesn't change no matter where the camera is. And this is not what happened in the real world, where reflections depend upon the viewer position and also from the viewer, the view direction. And on the left, I'm showing here the reflection after applying the local correction. So no matter what we do, what we store in our Cubemap, when we are dealing with Cubemaps in a local environment, we need to apply the local correction. Otherwise, we will not get what we expect. So now that we have gone through the concept of local Cubemap, I would like to introduce our new shadow rendering technique based on local Cubemaps. This technique is really simple, and I think you will be able to understand it just in the very moment. We need to apply this technique in two steps. During the first step, which is at the stage of the generation of the Cubemaps, we baked in the alpha channel of the Cubemap the transparency of the scene in such a way that when baking the Cubemap in the alpha channel, if in the pixel is completely opaque, we write in the alpha channel 1. And if that pixel, the geometry is fully transparent, if there is no geometry, for example, in the case of the window, so we write in the alpha channel of the Cubemap 0. So we build in the alpha channel of the Cubemap a map where the light can come through and reach the volume, the interior volume of our scene. This is the idea. At this point, we are not taking into account the number of light or the position of light. The only requirement is that the light should be outside of our volume. So it means this technique will be independent of the number of light and independent of the position of light. So what we need to do at runtime? So at runtime, we build in our vertex shader a vector from the vertex to the light position, and we pass that vector to the fragment shader as a variant. Oh, sorry. In such a way that we get the fragment to light vector already interpolated in the fragment shader. And what we need to do in this case, we need to apply the local correction to this fragment to light vector. If we apply the local correction, or after applying the local correction, then we are ready to fetch the texture from the Cubemap using our fetching function, using this new vector, the vector from the position where the Cubemap was generated to the intersection point, and we are interested in this case only in the alpha channel. If we get, the value we get is 1, it means that in that direction, that will be an opaque geometry. So that fragment, that pixel, will be in shadows because the light can reach that pixel. If in that direction we get, the alpha value is 0, so it means that in that direction there is no geometry, or the geometry is completely transparent and that pixel is lit. As simple as that. You can have the full source code of this technique in the ARM guide to Unity, as I explained before. So what we get is at runtime, when the light changes the position, the vector from the vertex to the light is automatically updated, and the shadows are automatically updated. And yeah, they were great just by fetching simple alpha value from the Cubemap, from our texture. There is another important feature of the shadows, which is the softness of the shadows. And we can reproduce this feature very easily. And I will explain how we can do that. Instead of fetching the texture from the zero-level min-map of the Cubemap, when baking the Cubemap, we will also build all the min-maps of the Cubemap. And at runtime, we will interpolate between Cubemap min-maps in such a way that we will blur the texel, and we will get that. But how we will do that? How we do that by trying to reproduce the fact that the farther away from the object, the shadows will be more blurred or more softer. So we use for that as a parameter a distance between the fragment to the intersection point. In that case, from the fragment to the point P or Q in that figure, in that scheme. So as you know, we need to use in this case the fetching function textCubeLOD, where the parameter, the second parameter we pass, is a fourth component vector, and in the fourth component we just pass a value which is proportional to that distance. In such a way that we, for example, what we did is we expose that factor which appeared there in such a way that you can, the artist can just control how much will be the softness of that shadows. And this is what we get. In the right slider is changing that factor. When the slide is in the lower position, you get completely hard shadows, and which is moving up, the factor is increasing, and you get the shadows are more and more softer. But look at this property. So when the shadows are close to the object, they are hard, and they get softer the more they move away from the object. So at this point, I would like just to list some of the benefits and some limitation of this technique. The main benefit is, I would say, that the quality of the shadows. They are very efficient to work with that. It is clear, but we get the shadows we get. They are very, very of high quality. Why? Because we are fetching every frame the texture from the same Cubemap. This is not what happens when we are using, for example, when we are rendering to texture every frame, because every frame the texture changes, and we will always see some kind of pixel shimmering or pixel instability. Not in this case. We get perfect shadows, very stable and perfect shadows. But the main limitation of this method, of course, is if related with the intrinsic nature of this. We are dealing here with a static Cubemap, so we can't render reflections from dynamic objects or from objects that change the shape at runtime. But we can solve this problem very easy by combining this technique with other more standard technique that render shadows at runtime. For example, the shadow mapping technique. And this is what we can. I'm showing here in this short video. You can play with this demo if you visit our booth too, where we are rendering here the shadow from the chess pieces, which are dynamic objects, are rendered every frame using the shadow mapping technique, and the shadows from the windows are rendered using the technique I've just explained, based on local Cubemap. Both type of shadows are combined in a single shadow picture. And just before finishing, I will just explain something that happened to me very recently when coming back from United Taipei, and that showed the power of this approach of local Cubemaps. This picture is taken in the corridor when I was going to the gate, and as you can see, there the reflection from the wall, and this is very typical use case for reflections based on local Cubemap. Right now, you can implement that in Unity using the reflection prop, which is reflections based on local Cubemaps. But there is an additional effect. As you can see there, the reflections are more blurred the farther away from the wall, the farther away from the real object that generates the reflections. And how do you think can be implemented that? It's straightforward. If we use the same technique I've just explained with shadows, and I did that as soon as I arrived home. I noticed that I just implemented the next day, and I got that in the same chess room. That slide is just changing the multiplier we're using as a factor in the fourth component of the vector. We are passing to the fetching function, text cube LOD, and you can see how the reflection is getting blurred the farther away we are from the window. It's just an example to show you the power of this approach. And finally, I would like to show you just a very short video about the demo, our latest demo, Ice Cave. You can come to our booth and you can play with the demo. It is an interactive demo. There we show the reflection based on local Cubemaps, refraction based on local Cubemaps. We combine several types of reflections. These shadows are implemented using the technique I've just explained. We got, again, there refractions. We got projected textures. We are rendering semi-transparent objects. We are using a lighting in custom shader. We are getting the information from a lighting. We are using very optimized bloom effect there. And we are using also very optimized fog effect. So there are more than 10 effects running in a mobile device thanks to the fact that they are very optimized. And we wanted to show that it is possible to get this level of quality in the current mobile devices. So yeah, I just encourage to come to our booth, and now I hand over to Carl. I'm sure you will enjoy his live demo. Thanks, Carl.
No, thank you. Keep clapping for me. Okay, I'm just gonna. So hi, I'm Carl Callewaert. I work at Unity. I'm very lucky to work there, but I'm super excited to work with ARM, and I learned a lot from Roberto, and I will show you why and what I learned. But I'm super excited. Voor de mensen die Nederlands spreken, ik kan het ook in het Nederlands doen, maar dan onder de ondertiteling moet staan, want het zal in het West-Vlaams zijn. Okay. Only the people from Belgium understood this. Okay. So let's look at this example here. So the benefit of listening to this little presentation I'm going to do is here that you're going to see how the technology from ARM is implemented in Unity. Okay. What we see is here is a simple scene, and the bazooka has an old material from Unity 4 in it, and the lighting is like in Unity 4. What we're going to do, we're going to use the Unity 5 features, and the Enlighten, but also the reflection probes and the physical-based material to boost it to a higher quality. But it also perfectly runs optimized on the ARM chipset. Well, what's really cool is that you don't have to do anything in the back end to make it all work. You just click buttons and it all does the magic for you. Okay, so let's look at this. Okay, I'm gonna go to here. The first thing I'm gonna do is talk about the skybox. And the light, the ambient light that contributes, comes from that. In Unity 4, we have a blue sky, and that's it. And that controlates the ambient material, the ambient lighting here. So look here, this is the ambient intensity. I can take it fully off or a little bit on, but it's a color. Unity 5, we switched it already. Click, and I can take a skybox here. Beautiful sky, and it's actually called Dutch skybox. It's not cheap, it's expensive. Okay. So we have the skybox running here, and what we're going to do is look here. We're going to change use a skybox as ambient lighting. Click, and right away, wow, a big improvement. Okay, looks nice. So you can see it here, off, on, off, on. Okay, everybody sees it? I think everybody's still a little bit hangover from the party. Okay. So we put it on here. No, look here, that's really cool. You're going to go here to the sky, and you're going to see how much it contributes actually here. I'm going to go here in the rotation. If I rotate this, you can nicely see the light coming in because the sun is there. It's nicely contributing to that. So here, the rotation, you see it nicely. Okay. What we also implemented was then the illumination, the bouncing of the light, the enlightened. And let me show you how that actually is nicely in there now too. Look, what we're going to do is here in this case, first we're going to take the ambient lighting off again. Okay. What we're going to do is we're going to go to our direction light. And this is Unity 4, but in Unity 5 we have the bounce intensity. The light can bounce around, so we can bring this up. So your artist can really tweak that to what it is. Now remember, this is all running real time. You can animate that real time, and it runs nicely on your mobile device. So we put it here on. Let's go back to the lighting. We're going to activate now the ambient lighting. And now nicely it becomes combined all together perfectly. Okay. Now another thing that we did is the physical-based shaders. And I think most of you are already familiar with it. But I'm going to show you quickly in Unity 4 in the inspector. We had the default material legacy here. This would be a diffuse material. Let's put it on standard material. Okay. The power is that we have here the metallic to it. So I can make it nicely fully reflective. Hey, let's say a reflective. Hello? Hello? You hear me? Yeah, okay. Don't blame me. Okay. So we're going to move it a little bit forward here. Okay. So you see nicely reflection. But when you look very carefully, what you see is you see the reflection of the skybox. That's it. I don't see the reflection of the environment. So I start to cry. Okay. I blame the artist. And this is now where it becomes really cool. What Roberto was talking about was the reflection probe. Let's create a reflection probe. Okay. We're going to go here to light, reflection probe. Okay. So the first thing that Roberto talked about was the position is very important where you place it. Look here. Look carefully to the reflection on the bazooka. If I would move that, you see that the reflection changes because it takes the sample at that position exactly where the reflection is. Okay. So what we're going to do is we're going to place it here a little bit closer to the bazooka. Okay. When I press play, okay, we have the bazooka. It has the reflection. When I walk, the reflection is there. But the moment I go outside that bounding box, exactly what Roberto talked about, I'm out of the bounding box, you see that the reflection changes back. I go in, and we have the reflection. So what we can do, we can put multiple reflection probes. I can just select it and be lazy and duplicate it. Okay, and I need to learn how to duplicate in Unity. Okay. And what we do is, we make sure that those reflection probes overlap. When they overlap, press play. Okay, so I have here, and I walk, and it overlaps to the other one. Okay, that's pretty cool. But now, what's the power is this? And that's what Roberto talked about, and I'm going to tell you how funny the story is. Because Roberto was showing that the reflections are moving. Okay. What you can do for that, there's a magic button here. And the button is here. I've set my reflection probe. And it's here, box projection. You just activate that button. Now, when the first time I did that and I press play, I see no differences. Okay, what does it do? So I went to our manual and I clicked on box projection, and it says box projection. So luckily I had the luck to meet Roberto, and then it nicely showing us examples. Oh, wait a second. When I press play and I walk, now you see nicely the reflection is moving. Okay, and we blend to the reflection of the other one. Okay, and I'm going to put that also to a box projection. The other one to a box projection. And look now, nicely, we have super optimized the reflection running. Blends to the other one, and it's nicely moving. This is all pre-baked, so it will work perfectly effective, very optimized on the ARM chipset. No problem at all. So the last thing I just wanted to point out is here that Roberto talked about the bounding box, and look, you can nicely adjust this in Unity. Look, in this we're going to adjust it so that the reflection is nicely correct. So you can go here to this button, and then you can adjust that bounding box to match it with your environment. Okay, select it, Carl. Okay, and then click the button again, and now you can adjust it. Yeah. Nicely there. This and this. Okay. Click on this. Okay. So now we have a perfect reflections, and when we walk here, walk in there, and do this. And the reason why I adjusted that, if you want to say like I'm going to do the interior fully reflective, like the material here, the floor, when you do that fully reflective, okay, nice. You're going to have perfectly the correct box projection working there too, thanks to this all. Well, that's fun. Okay. So that was a quick overview. You can see how the Enlightened really boosts you the quality, but also the physical-based materials. But you see that the technology from ARM, sharing the knowledge and working together, has really brought the box projection out to high-quality reflections. And I'm looking forward for more from you. So
thank you, Carl.
Thank you.
Thank you. Thank you, Carl. Thank you to all of you. Okay. Can we? Okay. Yeah, just to tell you very short that you can find out more information about this technique and other very highly optimized rendering techniques at malideveloper.arm.com, our website, and there will be you will be able to win a Samsung Galaxy Note 4 if you fill this form there, and we will do the ARM booth will be the So this Galaxy 4, no? So this one can be yours. So I think we are ready for questions. Yeah, we are ready for questions, if any, please. Yes, please.
I saw the demo you still use standard material, which you need to optimize the material.
Which demo? His demo?
Yeah, I use the standard hello. Yeah, I use the standard material that's totally optimized already.
Okay, also for mobile.
Yeah, totally optimized for that. Yeah.
Yes, please.
Yeah, so I wanted to ask, could you also have just like attach the reflection probe to like a gun or the camera, so you have one and it moves with the guy around?
So in the reflection probe, you can actually go and change a few things. The question is, can you basically move a reflection probe if you want? You could go to your reflection probe, and in the settings, I can actually quickly show it here. Okay. So when I select here the reflection probe, okay. So when I have the reflection probe here, you can see it's set to baked here in the options. In there, you can actually set it to real time, and then you can put the refresh mode on awake, but you can also set it to every frame if you want, and I attach it to an object for moving in that way. But of course, this comes at a very high cost. Yeah. I would be smarter. I would be like working in the Roberto style.
Yeah, if you update the reflection prop any frame, so the cost will be high.
Okay. I hear we have to wrap
Yeah.
up, so one question, and then, nope, okay.
Thank you
No
very
more
much.
questions.
Thank you very much. And I
you.
really encourage you to visit our booth. Thank you.